Hola a todos, muchas gracias por venir y gracias también a los que están conectados en streaming. ¿Tenemos personas conectadas también? Ok, bueno, pues buenos días a todos. Es un placer para mí estar acá en una nueva edición de los Inria Talks y hoy también con una delegación. I'm sorry, I will switch to English maybe. Okay, sorry. Okay, welcome everybody. It's a pleasure to have you here, and it's a pleasure also to receive today the visit of some colleagues from Inria, and also colleagues from the counterparts of our Chilean institutions in Chile and from Brazil also. Welcome. So it's my pleasure here to call to Oana Iova, which is an associate professor in the Telecommunication departments at INSA Lyon. Where she has been the faculty member since 2017. She conducted her research within the CITI laboratory as part of the Inria Agora research team at Inria. Her research focused on the design, evaluation, and experimental validation of energy-efficient wireless networking solutions for the Internet of Things, spanning both terrestrial and satellite communication domains. She has a strong experimental component in her work, leading test beds, prototypes, and real-world deployments. And she will be doing her talk in a tandem with Juan Fraire, which is the researcher at Inria, also friends, and guest professor at CONICET in Argentina, and also Saarland University in Germany. His core area of interest are near Earth and deep space networking and informatics, with more than 120 publications, etc. Lot of huge CV. So their part also, this Agora team is a very important part of the Inria Chile ecosystem. I just wanted to say that they have not only an equipo-proyecto, but also an AMSUD project, and I'm happy also to welcome their colleagues from the Chilean and Brazil institutions. And also they have been also taking part of our internship program. So I'm very happy that you're here, and welcome to this stage.
Thank you, Nayat. Hello, everybody. Today we have two main shows, so to say, presentation. I will first do a little bit of technical presentation in one of the technologies that are currently used today in terrestrial and in satellite communication for the Internet of Things. And then my colleague Juan is going to open up a little bit the different fields of research in satellite communication. To start, it was working 2 minutes ago, right? Thank you. I seem to have a running problem with these devices this week. So a little bit of background on the Internet of Things, so to speak, like a big panorama, because Internet of Things are today surrounding us, and we find a lot of application in a lot of different fields, such as smart buildings, smart cities, also everything that has to do with environmental, industrial application. And what is important is that whatever the application is, what we consider as being part of the Internet of Things is basically a network of interconnected devices that allows two things. One, to monitor the different events that can happen remotely, pollution, temperature, movement of people, and so on, but also controlling the devices remotely. So we are able to actuate different devices in response to the monitoring events and everything that happens in the environment where these devices are being deployed. As we have a lot of different types of applications, all applications also have different needs in terms of their throughput, in terms of their energy consumption. You can have devices that need to be energy aware for maybe 2 years or 10 years in function of the application and the places where they are being deployed. And also, we're going to have different needs in terms of robustness and latency to communicate with these devices. So there is not today a single technology that is going to answer all these needs for all the different types of applications that we have. So there is a plethora of wireless technologies, and you have to be careful when you're going to pick one of these technologies and apply it to a given technology. Today, it is a big group of these wireless technologies called low power wide area networks that differentiated themselves for all the other technologies because they manage to communicate over a wide area. So we can have a few kilometers of communication range inside of an urban environment. And this can go up to 20, 30 kilometers of communication in a rural area. And there are also technologies that are considered today for satellite communication, because when you are in remote areas and you have a clear line of sight communication to satellites in the low orbit, these technologies can communicate directly with the satellites. So they're very important in both terrestrial and satellite communications. I'm going to focus for the rest of the talk on one specific technology, which is LoRaWAN, and more specifically to the LR-FHSS technology, which is called long-range frequency hopping spread spectrum. So this technology has been introduced recently by Semtech, along with the most known technology, LoRa, for being deployed in dense urban environments, and also for the communications to lower satellites. Contrary to LoRa, which is a spread spectrum-based modulation, LR-FHSS is a GSMK modulation, which does frequency hopping within several lower sub-channels. So the packet of information that has to be transmitted is going to be divided into several small fragments, and then each of these fragments is going to be sent on different channels, hence the channel hopping part of the technology. The first part of the packet, which is called the header, it's the most important part, because this is basically where you have the device identification and the payload sites, and also this header is going to be the one that keeps this frequency hopping that you have to do over the multiple channels. So if you don't know the frequency hopping for a given packet on the reception side, when you are going to recover the different fragments, you basically don't know how to put them all together because you're missing the information that tells you how to assemble it. So that's why the header is extremely important. This part of the packet is not going to be fragmented, it's going to be sent as it is, and also it's going to be sent several times, because basically if you lose this information, even if you receive all the fragments, you're not going to be able to decode the packet. So the robustness is extremely important for the header. In order to decode the packet once you're going to receive it, it is important to have at least one of these header replicas that has been sent, and in function of the coding rate that is being used for the fragments, you're going to it's going to be enough to recover 1/3 or 2/3 of the fragments in order to reconstruct the packet. So that means that you can lose quite a bit of information and still be able to reconstruct your packet and recover your data. So that's a big point for these technologies when you're going to have to deploy it in dense urban environments, or even when you're going to have to communicate with satellites. So just to give you an overview, you can maybe ignore this part because this explains how your frequency is going to be divided into very small sub-channels. The important thing that you can get from this figure is that each of these lines is going to represent a very narrow subchannel. And then when you're going to have to send the packet, for example, let's look at the green rectangles that you see here. You're going to send the header, which is represented by this large green rectangle, on several times, each time on a different subchannel. And then the fragments of these packets are going to follow also smaller fragments on the different subchannels. And when they're going to be received at the gateway, once you get one of the headers, it doesn't matter which one of them, you can put together all these green packets and reassemble, all these green fragments and reassemble your packet. So there is a little bit of matching that is being done by the gateway. Now, the main question that we ask is that I have been saying until now that it's really, really important to get the header of the information, because that's where the sequence of the channel hopping is introduced. So can we still do something to recover our packet even if we lose the header? Because it has been shown that you can lose the header. There are several reasons why you use it. One of the reasons has to do with the fact that it's a much larger portion of the packet compared to the small fragments, and so it is more prone to interference and collisions, and you can lose it. What we can try to do in order to still get our information from the different fragments that we recover without the header is to try to do our own matching without knowing what the sequence is. And this can be done because there is a limited number of possible sequences that exist. So we have 512 possible sequences. And if we manage to model a little bit our system, then we can try to see if what we receive matches any of the 512 sequences that we have. So just checking. In order to do that, we model our sequences as matrices that you can see here for different types of sequences that are illustrated. Basically, you have the time. Each square is going to represent a given frequency channel at a given period in time. So when I'm going to send my packet fragments, if I'm using this sequence, each of the fragment is going to be sent in the first time slot on this channel, in the second time slot on this channel, and so forth and so on. So we have a bunch of sequences that are going to be used by different packets. If I am at the receiver side, what I'm basically going to see is a very large matrix with some slots that are being used on different channels. What I want to get out of this information is a decoded value where I can see, okay, these slots here, they belong to sequence number 3, for example. The following slots are going to belong to sequence 2, maybe. And by doing this sort of pattern matching is what is going to help me to recover my information, even if I don't know this particular sequence to which my fragments are going to belong. So how can we deduce from just seeing different fragments and not knowing which one belongs to which sequence to be able to get to this very colorful and nice matches that basically is going to tell me that all the blue slots belong to a given packet and all the red are going to belong to the other packet. So we did a modelization where we basically have defined a tuple that is going to tell me for each sequence the number of the sequence. So the first value is going to be the number of the sequence, the time slot at which this time sequence is going to start, and the length of the sequence. So I'm defining this tuple that afterwards I'm going to use to construct my matrix, and I'm going to model it as an ILP model in which the objective is to find the minimum set of tuples that can represent my matrix that I want to find. And I'm doing that with the condition that the tuple that I'm going to find uses a sequence that actually exists. So that's my, my condition there. That would be the optimal model that we are going to use, but you also developed a heuristic, which is defined as a greedy approach, to try to see if we are able to get results that will be close to what is given by our ILP model. So our greedy approach basically is going to iterate over all the time slots, over all the sequences, and try to see if this matches. So I'm not going to go through this algorithm here, but I'm going to give you a visual example of how the algorithm works. So this is my observed matrix of the different slots that I see that they are occupied. And what I'm going to do is that at each time slot, I try to see which channel is the channel that is being, that I observe that has been a transmission. So here there will be the second channel, and I see out of all my sequences, which sequence starts on the second channel. So in this case, it will be the sequence 3, and I'm going to put my sequence in my observed traffic matrix and see if the pattern matches with what I have there. If that's the case, it means that I have discovered the different fragments that have been received that belong to the sequence number 3. And then I do the same thing for the next slot where I see an activity in the channel. So again, I see an activity on the second channel in the second slot, and I try to see if my sequence that uses the second channel as the transmission matches all the other things that I observe. This is not the case, so it means that this is not a possible packet transmission. So forth and so on. I think you get a little bit the idea. What can happen also is that I can get a sequence where some fragments overlap. Okay, so I found a sequence, the blue sequence, and I found also the pink sequence that is here, and I have a fragment where both sequences use the same channel in the same time slot. So that means that most likely a collision happened here, because it can happen that the sequences are going to use the same channel in the same time. But that's not an issue, because I said that in function of the error correction mechanism that I'm using, I can lose up to 1/3 of 2/3 of the packets due to collision and still recover my packets. So I can just say that the fragments here matches my sequence. So this is a potential packet that I'm receiving, and I'll see afterwards if my receiver can actually decode the packet. Okay, so quickly, just to see a small result, because before I pass the word to Juan. So we did some tests where we looked at both the performance of our ILP model and the performance of the heuristic method that we proposed, and we tried to look what is we call it the detection effectiveness. That means out of all the transmissions that we have seen at our reception, how many real sequences I managed to I managed to recover out of those that have been transmitted. So this is the true positive matrix. So it means that the sequence exists and I managed to detect it in my matrix. I could also have false positive. So false positive means that I have detected a possible packet, but that does not actually, the sequence does not exist. So that would be a false positive. And then the false negative is that there are sequences that have been transmitted, but I was not able to decode it on my side. So there are several interesting things that we saw. First of them is that we have the exact time results for the heuristic method and for the ILP model. So we are managing to get very good results with the proposed heuristic. We have absolutely no false negatives in the results, and we get true positives, all the curve that is here, which gives us our true positives and shows that in all the cases, no matter how long our sequence is, so we have, I forgot to mention this, is that I can have fragments with, I can have packets with different lengths for the payload. So I will have from 10 fragments up to 19 fragments of my payload. So in both cases, we managed to get all, to detect all transmissions that have been taken place. But on the negative side is that we get quite a lot of true positives. So the question is, okay, we get a lot of true positives. Can we try to do something to reduce the true positives? But also, is there actually a problem, the fact that we get true positives? Because true positives means that we detect something that didn't really happen. And if we detect something that a transmission did not take place, this can actually be resolved very quickly by the receiver, because each packet has a value which is called a CRC, a constant redundancy check, which basically is going to help match and say, okay, this is a real packet or it's not a real packet. So even if I have true positives, the gateway is going to be, the receiver is going to be able to just drop the packets without any issues. So that's what I wanted to talk to you today about. So the LR-FHSS technology, to have a little bit of background and knowing about how this technology works, but also a proposed method to try to solve the problems of packets that are being sent with the headers that are being lost, and show that with quite straightforward methods, we are being able to recover our data packets, even if the most important information that is stored in the header has been lost. So that's for the first part of the presentation. I think we can take the questions later. I'll pass the word to Juan, who's going to talk about satellite networks. Thank you.
Thank you, Anna. I get the applauses. You give the talk, I get the applauses afterwards. Yes, so let's move on. Yes, so I'm going to zoom out a little bit. So Anna gave a very nice presentation about a very concrete, specific, and important technology for satellite IoT. But I'm going to zoom out a bit to the broader scope of satellite communications and networks. So those that are a little older like me will remember that even though we are living a very nice moment for satellite communications now, thanks to Starlink, Elon Musk, and SpaceX, and rockets being reused, and so on. But back in the 90s, there was already a very good momentum happening. By looking at these constellations that I'm mentioning here, Globalstar, Iridium, Teledesic, this might trigger some memories for those that in the 90s were already starting to see some very early satellite constellations being deployed that were effectively like Globalstar and Iridium became operative. They started to provide services. But interestingly, many of them went into bankruptcy by the end of the 90s. So Iridium and Globalstar both failed, even though they had 66 and in out of 24 satellites in orbit. Teledesic was on the development, on the roadmap. Teledesic was funded by Bill Gates back in the 90s with 300 satellites in orbit to provide service. Very similar to the shapes that we see nowadays for Starlink, right? So what happened? So the business model was essentially not there yet. So the technology was happening okay, routing was happening, data was getting transported over these networks, but unfortunately the business was not up to speed, and billions of losses happened. And since the early 2000 onwards, for almost 20 years, investors basically ran away from space businesses until now. Now we have the largest companies of the planet investing heavily in space networks. So it seems that this fear from the 90s happened, but now it's gone away, and there is a new revival, it seems, for satellite networks. Of course, Starlink is the rock star of this, but also Kuiper from Amazon is on the roadmap. There are a few hundred satellites in orbit already. They're planning to go close to Starlink very soon. And OneWeb is also the equivalent actor on the European side. What is enabling this new trend of satellite networks? Launcher, reusability, and also specialization of electronics. These are no longer space-grade, radiation-hardened electronics in many cases, and this is allowing to cost reduction, and it's allowing profiting from the economy of scale. And in principle, this seems to be good revival of what failed back in the 90s. Is this sustainable in the long term? Maybe. There are two considerations here. So we're talking about economics, where, so we are profiting from this massive scale. We have rocket reusability. This is allowing lower cost and so on. And also geopolitics is on the way, right? So space networks are a geopolitical asset. It's not only about business models. This is something different that with respect to the 90s, where in the 90s, we were just getting out of the Cold War. Geopolitics was there, but this was quite a different scenario that we have nowadays. So now space assets are also a strategical asset that might be justified to be there, not just because they are economically viable. But in any ways, the question remains, are we going to stay in this space momentum for the years to come? I guess this is yet to be answered. But in many ways, for us, on the research perspective, I think this is a great opportunity to think and do research on how do we conceive space networks that are sustainable, resilient, they are sovereign, and they have all the characteristics of performance characteristics that we need. So maybe from the research side, we can also approximate and look into the space networks and ensure that we'll remain operative for the long run. So I'm going to touch on very specific research topics that we work on and that we believe are important for space networks to actually, as I said before, remain alive. So one of them is access. Access is a key opportunity for space network that is also being quite different than the past, where we are now starting to talk a lot about direct-to-device. This term that is around a lot has to do with the phenomena that instead of connecting devices to a terrestrial ground station like we were doing on a day-to-day basis here on mobile networks on ground, the direct-to-device paradigm says we're using unmodified devices like smartphone or IoT devices to reach out to a low Earth orbit satellite in a direct manner without any intermediary that acts as a repeater or anything like that. So we can just use our smartphone when we don't have a terrestrial gateway to reach out to a satellite directly. This means that you could potentially have service on the mountains, on unserved regions, and this is being a huge driver case for satellite networks nowadays. This will allow global coverage in the underserved areas and also discuss disaster recovery, and it's a huge trend, and it's also getting the interest of many companies in the planet. So you will see here some examples. So those that have iPhone, they have seen the satellite icon eventually when you're out of service. So Apple iPhones are already having chipsets that are allowed to connect to LEO satellites. Specifically with Apple, we are connecting with Globalstar satellites. But also Starlink is pushing forward heavily services that you can connect with your unmodified smartphone to the satellite. We have startups like AST putting together satellites. You can take a look at the size of that antenna there, which is what you actually need to have good performance from a very far away satellite to a device on your pocket that was originally designed to connect to a ground station just a few kilometers away, but not 600 kilometers away like a LEO satellite or low Earth orbit satellite can actually be. We do a lot of research in this context. This is just one example of one of the projects we have. Is another equipo-proyecto we have at Inria with UC Berkeley. This is a recently published paper in Hotness where we actually try to understand to which point this type of direct-to-device access are really the solution to bridge the digital divide. I point you to the paper, you can take a look, but I can advise you the answer. The answer is no. You want to know why? I suggest you to go and read the paper, but it's actually the mechanisms that you need, the energy that you need, and the free infrastructure that you need. Our calculation shows that you need constellations in the order of 80,000 satellites to achieve what a reasonable direct-to-device capacity would need. This brings sustainability aspects a lot in the table, economical aspect as well. So this is just one of the examples of things we do. Also, in the case of IoT, when we are not looking into broadband communication, so small packets, low bandwidth, low data rate, low energy, things are a bit different. Oana presented a very good example of a technology that is used for this type of communications. The relaxation of the data rate also relaxes heavily the infrastructure you need for IoT. And in the case of direct-to-device IoT access, we can also start talking about very small satellites like nanosat or CubeSats, like the one we see there, because of the low footprint of these technologies. The energy consumption is so slow, the data rate is so slow that you can come up with solutions with very small satellites for very small devices. This is an example of Lacuna. It's a startup company from the UK that they actually do direct-to-device IoT. So you can use state-of-the-art protocols and achieve connection from very small devices to the satellite directly. That is actually quite attractive to the point that many startup companies are actually getting funded and actually start to compete in the market with different technologies, different approaches to achieve this direct-to-satellite IoT, as we coined it as a research. Of course, this is something we're doing since quite a while. We have our stereo project, ANR project in France, looking at this heavily, partnered with Kinéis, one of the French companies. It's a spin-off from CNES, the French space agency. They are also looking into this topic intensively with us. And you can see this acronym here. So long-range frequency hopping, the technology that Oana just presented. We also have a foundational paper that was very well cited, that we discussed the trade-off and the opportunities and advantages of direct-to-satellite IoT. And we also develop tools to make performance evaluation and estimate how this network can actually operate. And these are open source tools that are publicly available for everyone to use. The second topic on research that we take care of, and I think is one of the key enablers for these networks, is the backbone part. So the access is what you get the data up to the satellite, right? Either broadband or IoT, your data is there. Now the question is, how do you transport that data to the internet? So the classical approach is this one over here. It's kind of a bent pipe, is the classical term, where namely your device get your data to the satellite and your data just go down to whatever ground station available is there. That is good, and that is used heavily now. Starlink mostly operates in this way in the majority of the cases, because Starlink has deployed ground stations pretty much everywhere in every region they're providing services to. But if you're in the ocean, if you're in the pole, or if you are in an area without a ground station nearby, then you cannot approximate the data transport that way, but you need to exploit what are known as inter-satellite links. So data that is transported from satellite to satellite until you get to a point where you have your ground station there. Transporting data over inter-satellite links is quite challenging, mainly because these low Earth orbit satellites orbit the planets every 90 minutes. They have a velocity in the order of 7 kilometers per second. So it's super fast. The dynamicity of this network is super challenging. So these links over here changes in time very often. and the topology of the network becomes extremely hard to handle. So this raises link scheduling problems. So to which neighbor I am going to connect to at any moment. Questions about routing, which is the next hop I should use to send this packet I received. Congestion problems, my memory might be full, my link might be overbooked. How do we deal with that in such a dynamic network? And function placement, where we are deploying like functions in individual satellite. How do we orchestrate this? This is a very big problem. We also take work on intensively. Gregory, I'm highlighting here, is one of my PhD students in Germany, in Saarland University. And here we work had made several contributions in the topic of routing for this type of systems that exploit the know-how of the orbital mechanics. So these are routing mechanisms that takes into consideration what are the orbital trajectories of the satellite to determine which is the best next hop. We have also an INSA project on AI applied to routing on satellite constellations, where we were able to test which are the limits of AI for solving this routing problem in satellite constellation. There is a reference paper there, very interesting with the findings. We also make a lot of work on transport layers. So once the routing is decided, so what happens with the congestion mitigation mechanisms that operates on top of the path that is formed on the satellite link? And to this, we have made several evaluations, and we also have contributed with tools that emulate the link, the multiple hop links that you observe and perceive from ground, and you're able to test how the different transport control implementation operates in realistic satellite systems. And we have also validated this with Starlink as well. We have antennas in Argentina, in Germany, in France, that we are constantly measuring the network, and we are fitting our tool to imitate what really happens in such a system. Then another thing that also motivates us a lot research-wise is the same problem, but looking farther beyond the low Earth orbit. We are talking about deep space. And nowadays, we have a lot of projects around, in the case of Europe, the Moonlight project is driven by the European Space Agency, is aiming to deploy the first lunar network infrastructure. And the questions are the same question that we have for the near Earth orbit constellation, are multiplied in terms of complexity to address such a lunar network. And the reason for that is essentially the huge distances that are involved. So the moon is 1 light second away from us. And 1 second, even though it seems very, very fast, protocol-wise, it's really a problem, right? If you send a packet and 1 second to get to the destination, 1 second to get back, that feedback loop is basically no good to operate. We are just in the border of limit of what can be reasonable for internet performance. And not to mention when we are starting to talk of connectivity infrastructure to Mars, where the one-way latency time can be in the order of 20 minutes, depending on the orbital position of the planet. This forces us to think on persistent storage in nodes, which is drastically different on how internet operates, where intermediate nodes, they have very little buffers just to compensate for congestion on the way. But in the case on interplanetary systems, you need persistent storage to keep the data stored until, for instance, you go out of the eclipse situation in another planet, and this essentially forces to rethink intensively how internet protocols really operate and how they are designed. So this is also quite a central topic for my research. This comes from my PhD moment. So I have a lot of cooperations with Argentina here. We have a cooperation also in China doing topics on deep space. And also recently in Canada with Jason, a new PhD student, I'm starting to supervise on scheduling laser links from Mars, for instance, in this case. Routing is a problem. Routing under uncertainties. What happens when links are uncertain is also very different to what we're used to see on the internet. And also quality of services and other examples I have here to share with you. I think this is pretty much my last point I wanted to make, and it's also something I'm very happy that we started to work on Space Cloud a few years ago, because now it's something that is getting more and more popular in the media. Why? Because at the very beginning, Kuiper, which is the constellation that will compete with Starlink, the main differentiator factor they have with Starlink was that they are going to offer onboard computer in Amazon satellites. You know, Amazon runs these huge data centers everywhere. And the key enabler that they show to the public that we're going to use to fight Elon Musk was to offer the capacity to deploy small containers in their own satellite, such that your device, when connecting to the satellite, you get a very low latency response from whatever application you're running up there. Now, Starlink has publicly mentioned that the V3 or V4 version of their satellites are also going to have onboard capabilities, which means that when you deploy your container in the cloud, you will have the option to run your container on board of a satellite, so you are closer to the user and you can enable very low latency communications. And many years ago, we started to design how would the space cloud look like? What are clusters of compute nodes that are connected in an opportunistic manner in near Earth and deep space? And there are two key axes here that I want to comment on. So one of them are orchestration methods, which is how do I choose the optimal satellite to deploy a given task or a given container to? And the other question is adaptation of existing DevOps infrastructure to really achieve this. So Kubernetes is one of them, and we are looking into Kubernetes a lot in the context of Dark Soul project. Is a project we have in the under a mission project. It's a larger project, so we have that we look about how do we can adapt the Kubernetes. It's an open source implementation so that we can tolerate latencies and disruptions in the deployment of the container process. And also in the case of orchestration methods, we do a lot of algorithms and optimization methods to choose optimally where to deploy a given application in a given satellite. This is also a task from Camilo, one of my PhD students as well. Then finally, which I believe is the most challenging part, is not access, backbone, or space cloud, but the most challenging part, I believe, in space network is about standardization and the community and achieving consensus. This is the hardest thing, and this is why you see I have cooperations with China, I have cooperation with US and so on, because my higher level objective is for people to achieve consensus on how things should be done, with the objective of repeating the experience of the internet, that everyone speaks the same protocol, and therefore we can extend effectively the internet into space. I participate intensively in IPNC and CCSDS. These are standardization institutions for interplanetary and space systems. But more recently, I'm getting more involved in the IATF, which is the Internet Engineering Task Force. IATF is where all internet protocols are standardized. And we are interacting quite a lot with the DTN, the TIPTOP, and TVR groups. These are groups that looks at delay tolerant networks for deep space. These are people that are trying to adapt IP, the current protocol that connects internet, to tolerate latencies and disruptions as we have in space. These guys are looking into routing, and I'm recently chairing the space research group, which tries to have like a broader view and coordinate between the different groups the key fundamental challenges and architectures that we should have in mind for achieving highly connected space networks in the future. So there is a revival on the way, but there is no guarantee that this revival will stay, right? And we are trying to do what we can from the research to have the tools on the table to achieve this. So for this, I mean, addressing these fundamental challenges is out of the essence. And this is why I briefly touched on access research, backbone research, compute research in the context of space cloud, and also what I believe is the core challenge. This is why this one is in red, which is achieving a consensus on an international scale on how to make these space networks actually stay and continue serving ourselves. So thank you for your attention. We're open for questions. I think we can check questions together here with Oana.
Questions, don't be shy. Don't be shy.
Okay. Thank you for your presentation. I would like to ask you, you mentioned swarms on some place over there. What happened with them? They were going to revive sometime, or just they got eaten by the Starlink?
Swarm, the company, you mean? Yeah, so Starlink bought Swarm a year and a half ago, or 2 years ago, something like that. Yesterday we have a very nice presentation in Miguel's place there from a student that is capturing packets from the satellites. What I know is that the system is operative, as far as I see.
Still
operative. But the real intention for Starlink getting this company was to get the spectrum that they have.
Oh,
So it's a spectrum acquisition, actually,
What
not
a
really
shame.
the company or the infrastructure. Yeah.
okay, thank you.
Questions? Oh, yeah.
Thank you. Thank you for the presentation. I have a question for Oana about LR-FHSS. So, and how is the relationship with that technology and the spreading factor? Because it seems we don't use spreading factor because LoRa is the kind of the key aspect of LoRa.
Yes, so it has spectrum in the name. It has nothing to do with spectrum. I think they keep the name just because it's sister technology with LoRa. It's a GMSK modulation, which is used in a lot of also satellite communication previously. But we don't have any spreading factors, parameters, or anything that is more LoRa-like, so to say. So it's just Gaussian shift keying.
Just a follow-up,
Yeah.
but it's enough for satellite to Earth? I mean, like we used to consider like the largest speeding factor. So here is equivalent to
So if I did some experiments where we were comparing LoRa and LR-FHSS in exactly the same environments, and you get the same communication range as you would get with spreading factor 11 or 12. So that will be the equivalent. You get a little bit more. You can get a little bit more of data rate if you're using the not much, but a little bit if you're using the smaller error correction part of it, because you have 1/3 and 2/3, so different error correction types. If you use the smaller one, you get a little bit more of data rate.
Interesting. Thank you.
Thank you.
Questions? Maybe online? Can you check online?
No questions online.
Yeah, so I mean, since I do research in AI, most of our group also kind of in that perspective, I would like to know like what is the current state of the art in terms of that, or what are you doing, or what other people are doing in terms of your field in like applying AI techniques in your field. Like, so I see a lot of things that are possible to do. I know modeling like using graph neural networks, or maybe in the scheduling or power consumption or something. So can you give us also like doing model inference on the edge, maybe also, but can you give us a little bit of an overview?
Okay. I start a little bit maybe on the IoT part and on the LoRa LR-FHSS technologies. So there are AI tools that are being used in order to configure the radio on the emitting devices, on the transmitting devices with the right parameters. You mentioned LoRa and spreading factors, so that would be really how to optimize the communication parameters to get the least energy consumption, but still keep the robustness of the technology. There are some works also that look at trying to figure out the traffic, the usual traffic that you will get, and recover the data when you have lost parts of it due to collisions, because you know approximately where your data was. It's covered with a lot of noise, so there is AI techniques that are working on that. There is also, I didn't talk here, but there is also an important part that has to do with the downlink communication, which goes from the satellites towards the end devices. Carlos here he's looking on AI related technologies for the scheduling of packets, and that it's even more, he's looking at terrestrial IoT for it, but then it's get much more complex when you have to do with LEO satellites and constellation and the information that has to travel. You also have to take the routing into account. So it's much more complex on that. So these are a few fields that AI is used on today. For satellite IoT specifics, I let you complete for the rest of it.
So I like to, when people talk about AI, I like to split between machine learning and not machine learning. So optimization-wise, everything we do is optimization in the end, right? So we are running exact optimization or heuristics or some type of algorithms to compute routes, to fight congestion and so on, like what I showed. But in terms of learning, in the case of space, it's a bit more tricky, because what happens in space is that orbital dynamics are pretty much deterministic. So you know where a satellite is going to be with a very high accuracy, but thanks to mathematical models and so on. So topological wise, there is not much to learn, right? Everything is well studied. We have good models for that. We don't need to train any model for that. And thanks to that determinism, in general, most of the problems can be framed as a classical optimization problem. You know what's going to happen. And given that you know what's going to happen, then what is the best option? And what is the best decision to make, right? So the place, in my opinion, for learning in space is quite contained to phenomena that are not exactly deterministics. Like, for example, traffic shapes, as Oana mentioned. You can, of course, consider like failures as a potential uncertainty pattern that you want to learn from or fit that pattern prediction. Yeah, anomaly detections and this type of stuff. But the classical space industry will say, well, they typically over-design satellites so that they don't fail, right? So the failure probability is so low in general that that there is not really room for learning failure patterns, honestly. Traffic-wise, maybe there is an option. So in my opinion, machine learning, I have to review a lot of papers about machine learning for space. I have to say most of them are very well unfunded, because in most of the cases, you know a lot of things. You don't need to learn things. You learn them already. We have good models. So I'm quite critic about the ML community when applied to space, especially when we start to see models that are either reinforcement learning models that learn on the way. So during the satellite lifetime, you are reinforcement learning something, and that is a no-go from the very start. No one in this planet will launch a satellite to be trained while in orbit, right? The money that costs to deploy such an infrastructure makes no sense to run a reinforcement learning live. Yeah, you can run it offline, you can train it offline, that works, right? And likewise, training model on board, right? So now many people are saying, yes, I trained my model on board of a satellite, without even really realizing that an onboard computer of a satellite is an extremely expensive machine, not considering the fact even that in space you don't have air, so therefore you don't have dissipation capabilities up there. So you cannot run a GPU in space efficiently. You need to clock it down so that your heat dissipation can actually go through the metal infrastructure of a satellite and get rid by means of radiation. You cannot put a cooler in space, right? So, my personal take on AI is, if we split optimization and learning, then optimization is the way to go. Learning, there are some small room to it, but very well justified, in my opinion, or in some specific cases. That is my take.
Yeah. Questions? No? Okay, so.
You don't want to get recorded.
No, you say optimization, you touch his heart.
Okay.
So join me to thank Joana and Juan for the fantastic talks. And I hope we can have some time now to have a coffee and discuss a little bit more. Okay, thank you.
Yes.